This video will serve as our introduction to joint distributions, and joint distributions are a way of studying more than one random variable at a time. So for example, imagine that we had random variables x and y, and those are variables whose values depend on some sort of random process or chance, and we want to study how the values of x and y vary at the same time together. And so we want to study them jointly. And this is just the tip of the iceberg about measures of joint probability. There's ideas of independence and correlation, which we are going to work up to. But this is just the very, very introduction to how to study two or more random variables at the same time. And we're going to study, first of all, we're going to look at the joint probability mass function, joint PMF, and that is for, just like it was for a single variable, for discrete random variables. And we're going to look at an example, first of all, before we give any definitions. So let's read through the example here. So a grocery store is having a sale on jars of peanut butter and jars of jam. But due to limited quantities or whatever, for whatever reason, customers are limited. They are limited to buying at most 3 jars of peanut butter and at most 1 jar of jam. So the table below, this table down here, the table below shows the proportions of customers buying different quantities of each item. So, for example, if I looked here, I would say that 14% of customers bought 1 jar of peanut butter and 1 jar of jam, whereas 12% of customers bought 2 jars of peanut butter but no jam, right? So this table gives us different proportions of customers buying different items, and the quantity of each item can be viewed as a random variable, right? Those variables have different values that they can take. There's a process, a random process, with the customers coming in and what they come in, let's say, randomly, and have random desires for peanut butter and jam. When a customer comes in, you don't know what he or she is going to buy. So we can view these, let's say, x as the number of jars of peanut butter bought by a customer, and y as the number of jars of jam bought by a customer. And so this table then gives us the joint probability mass function for x and y, and so that function is typically notated p of xy, and it is the joint probabilities for x and y. So how can we use this? Well, let's go through and do a couple of simple questions here. So give the probability that a randomly selected customer buys 2 jars of peanut butter and 1 jar of jam. 2 jars of peanut butter and 1 jar of jam. That would be the saying p of x equals 2 and y is equal to 1. So the and we typically just write as a comma, right? And another way of writing that would be the probability that x equals 2 and y equals 1. But for a joint mass function, we tend to write that probability with a comma. So that's saying that x is 2 and y is 1. That's like saying p of 2, 1, which in the table is right there. Excuse me. The probability that a customer buys 3 jars of peanut butter and no jars of jam. So the probability that x is 3, y is 0, p of 3, 0 in the table is right there, 0.08. So those are simple questions. What if I ask something a little bit more involved? What if the probability that a customer buys 3 items total. So in terms of x and y, that would be like saying the probability that x plus y equals 3. Well, there's more than one way that that can happen. X could be 3 and y could be 0, or x could be 2 and y could be 1. So we take those two values, the value p of 3, 0, and p of 2, 1, we add them up to get our answer. And another kind of more involved question, what's the probability that a customer buys fewer than 2 items? Right? So there could be an inequality in our probability expression. What's the probability that x plus y is less than 2? So there are 3 ways for that to happen here. There are 3 ways the probability that x is 0, y is 0, x is 1, y is 0, and x is 0, y is 1. So add those probabilities, and those probabilities come straight from the table, and we get the probability 51% chance that a customer, a randomly selected customer, buys fewer than 2 items. So that's all pretty intuitive. That's all pretty intuitive. You might remember from your discrete probability of a single variable that a table of values gives a nice way of representing the PMF. And as it does here, the table of values, a double table of values, is a nice way of representing the joint PMF of two variables, x and y. So let's go and be a little formal about this now. Let's look at this definition from our textbook here. And so let x and y be two discrete random variables on some sample space S of an experiment. The joint probability mass function, the joint PMF, P of xy, is defined as this. P of xy is the probability that x is some small value x and y is some small value y. Those are the numerical values, x and y, that go in there. The discrete PMF, the joint probability mass function, must satisfy two characteristics. One, it is a probability, and so as a probability it must be greater than or equal to 0. And 2, if we sum up over all x and y values, the total sum of all of the probabilities must be 1. Right? That's the total probability, that must be 1. And then, so that we looked at, if you looked back at the table and added up all those values, if you had looked back up here and added up all the values in this table, you would in fact see that they do add to 1, and they are all positive. So we have a valid joint PMF. Now, further down, they say the following: let A be any particular set consisting of some subset of pairs of x, y values. For example, they give the example x plus y equals 5. We had x plus y is 3. Or the max of x, y is less than or equal to 3. We had x plus y is less than 2. This set A, so this is what we had called A, this subset of all possible pairs, the probability that x and y is in this subset is the sum over all pairs in that subset of the probability. And that's exactly what we did. That's exactly what we did up here. So that is all pretty intuitive. That is the discrete case. While we are being formal, let us talk about the continuous case. The continuous case. So now let x and y be two continuous random variables. A joint probability density function, yes, density, not mass, is f of x, y for these two variables. Satisfying f of x, y has to be a non-negative density, and the double integral over the entire plane, the double integral of over the entire plane, the total probability has to be 1. And for any two-dimensional set A, which is some subset of the x, y plane, so this is starting to look familiar from our multiple integrals. The probability of that x and y are in that subset is the double integral over that region A of f of x, y, dx, dy, or dy, dx, depending on the order of integration that you choose. So everything that we learned about double integrals is going to come into play here with joint probability density functions. And they give an example. If A is a rectangle, if it's a rectangle, which we would have written AB cross CD, well, then the probability that our two variables x and y, the pair of them lands in that region A, is the same thing as saying the probability that A is less than or equal to x is less than or equal to b, and c is less than or equal to y is less than or equal to d, which is our iterated integral just over a rectangle. So let us go and look at an example now, an example using the joint probability density function, because we're going to be talking about continuous random variables. So this example here, gasoline at a service center gets stored in a huge tank. The gas is refilled at the beginning of each week, but not necessarily to capacity. We're going to let x be the proportion of the tank that does get filled, right? So the tank may be filled on any given week to 75% of its capacity, or 80%, or whatever, depending on supplies. We're going to let y represent the proportion of the total capacity, not of how much was delivered, but of the total capacity of the tank that gets sold in a given week. So x and y are obviously two random variables. The value of x depends on some random market forces or supply chains or whatever. Y depends randomly on people who come in to purchase gasoline. So these are random variables, and they vary together. Obviously, you can't sell more. You can't sell more gas than you have, and so there is some sort of joint density function. The way that these variables vary together is given by this joint density function here. F of xy is the k times x over this region. And so we're going to take a look and explore that in just a second, and 0 elsewhere, right? So you might remember some similar things for density functions in the single variable case. The density doesn't have to be positive everywhere, it just has to be non-negative. There can be a great portion of the line in a single variable case, of a plane in the two variable case where the density is 0. So let's explore this area here, which I would call the support of xy, the place where there is non-negative density. And so let's take a look at these notes over here to explain why this region makes sense. First of all, x and y are proportions, and so they should be between 0 and 1. So that explains the lower value here and the upper value there. They are proportions, and so they're between 0 and 1. Well, why this middle part? Why? Why is y less than or equal to x? Well, y, we'll remember, is the proportion sold. Proportion of the entire capacity sold. Well, it can't exceed the proportion that was filled. You can't sell more than you have, and so y has to be less than or equal to x. So that makes good sense there. That makes good sense, this restriction on the values that y and x can take. So questions that we are asked then. First of all, to draw the support, to draw this region, right? Draw this region here in the xy plane. We are then asked to find this value of k. Find that value of k up there using the properties of the joint density function. And then C, find an actual probability. Find the probability that the tank will be filled less than halfway but then more than 1/4 of the total capacity will be sold. Okay, so let's go through those in order. First, A, draw the support. Well, here it is. Here it is. So we know that this is between 0 and 1. And y is less than or equal to x. So y is equal to x is the boundary here. And if y is less than or equal to x, we have below the line y equals x. And x can be anywhere from 0 to 1. So the support of x and y, this region here, is this triangle, is this triangular region down here. And the density then is 0 outside, right? The density is 0 outside of that region, and so probabilities are 0 outside. B, find K. I was about to read C. Find K. So what do we need to use for K? Well, we have to use this property that the integral over the entire plane of the density has to give 1. It's the total probability. So if we go over just the region that is non-zero, well, we can set up a double integral. X goes from 0 to 1. Right? If I were going to set up the inequalities for this region, I would say that x goes from 0 to 1. And for a fixed x value, y goes from 0 to y equals x. So that is the value or the bounds on the inner integral. And then the inside, well, that's just our density function, right? That's the f of xy, which was sitting up here, the f of xy. So that integral then is going to give me something that I can solve for k. So we're going to evaluate that integral. It's just the same old double integral that we've done for a couple of weeks now. Now that we have the setup based on probability, it's just evaluating a double integral. So power rule, which gives me a value, an integral in terms of x, evaluate that, you get 1/3 k is 1, and so k has to be 3, so that the total probability, right, the total probability when you integrate the density function is 1. C. Question C asks us to find the probability that the tank will be filled less than halfway. So less than halfway, which is a variable on x, a measure on x, that x is less than 1/2. And that more than 1/4 of the capacity will be sold, which is telling us something about y. Y was how much was sold. More than 1/4 has to be sold. So if we come back down here and translate those into restrictions on x and y, we are talking about the probability that 0 is less than or equal to x is less than 1/2, and that y is greater than 1/4. So if we go down into our region, here, our triangular region, and we graph these things, then when we graph y is greater than 1/4, well, here's 1/4. If y is greater than 1/4, it is everything that is greater than 1/4. But at the same time, I want x to be between 0 and 1/2. So if x is going to be between 0 and 1/2, then everything here in the region is x is between 0 and 1/2. But we want those to be true at the same time. That's what this comma means, and, which is the same thing as the intersection. So we are looking at where those two regions intersect, which is this triangle now that I am shading in blue, where the red overlaps the green. That is our triangle right here of intersection. So that triangle we are going to set up. We want to integrate over that region, which using the definition that we had above, right? We said if A is some two-dimensional, well, it says rectangle here, but some dimensional subset A, right, of the support, then this triangle in blue is the subregion A that the definition is talking about. And so this integral here, the integral from x is 1/4 to 1/2, 1/4 to 1/2 of dx. Y goes from, well, it goes from 1/4, you can't see that now, I've written over this region in so many different colors. Y goes from 1/4 to x. So y goes from 1/4 to x of the density function. If we fill in the k value as 3, that's our density function. Evaluate that integral, so I skip the steps, and you will find here the probability that x is between 0 and 1/2 and y is greater than 1/4.